Welcome back to Deeksha Vedantu YouTube channel. I hope you all are doing great. I'm Aditi, your physics faculty, and today I've brought you a chapter, Magnetic Effects of Electric Current, in one shot. Now, if you are someone who has not understood the chapter at all, who does not understand why this electric current is affecting my magnet and its magnetic field and everything, and it goes straight over your head, then this video is for you. Although if you are someone who just wants a quick revision of this chapter, there is another video, a rapid revision of this chapter that we have put in our channel also. You can go ahead, check that link in the description. Now, to understand this chapter in depth completely, this is the video for you. So let's start without any delay. So what this topic says is magnetic effects of electric current. Now, what the first word is magnetic. What is a magnet? Let's understand in a bit conclusion what is exactly a magnet is. So let's just look at this video. Okay, what is happening here? I have a magnet, it's north and south poles, and because of that this compass is getting deflected. But the main thing that you need to look here is, if I put south pole, the red part of the needle is getting deflected in this direction, but if I put north pole in towards the direction of the compass, another side of the needle is getting attracted or towards our magnet. So what exactly is happening, why is this happening, is what exactly we are going to study today. Now, if you have some fridge magnets in your house, definitely, right? Or you've played with this, we used to call it chumbak. These are magnets in our school days. I don't know about you guys, your generation, but we used to play this with this in our school and everything. What are these? These are magnets because they stick to the fridge. Why do they stick to the fridge? Why do they don't stick to my wooden door? Okay, why does these magnets, when you place it in a certain direction, they repel, but if you reverse them, they start attracting each other? Why? All of this is because of the properties of matter, that properties of magnet that we are going to study today. What we are going to look into is magnet and its poles, and magnetic field lines. Now, the chapter is magnetic effects of electric current. So we are going to say how the magnetic field is getting affected due to a current carrying conductor. We'll see different kinds of shapes of current carrying conductors, different rules on to see the direction of magnetic fields, the direction of force due to the magnetic field, and everything. So sit back and relax. This is going to be a very, very easy topic and chapter. Just don't let it get heavy on you that this chapter is very, very hard, I can't understand this. It's very easy. Just say it's very, very easy, and I'll do it in this one shot. Okay, let's start with the chapter. The chapter has a very important scientist named Hans Christian Ørsted. What he was doing some experiment one day with electric current, with wires and batteries and all, and he accidentally placed his compass needle near that whole setup. Now, what he noticed, by mistake he did it, okay, he was not intentionally placing a compass near a electric wire. What he noticed, that whenever he switched on the current, the needle is getting deflected. We saw how the needle was getting deflected, right? In this video, we saw that this needle is getting deflected. So when he placed this compass over let's say parallel to this wire, and he switched on the current, he saw that the compass needle is getting deflected. So he was very stunned. What just happened? He accidentally discovered it, but with the help of this, we got to know that magnetism and electricity are related phenomena. The things that were happening, the compass needle that was getting deflected due to the electric current, both of them are related phenomena, and then because of that we discovered various technologies which are such as radio, television, fiber optics, through which the network comes in our houses, the internet comes in our houses. So we need to study first what is magnet, and it has something called poles. Let's see. So a magnet is a object. It is an object that attracts certain materials like iron, cobalt, nickel, only these kind of materials. It won't attract wood. Why? Because it's just its property that you'll study later, why exactly this magnet only attracts iron or cobalt or nickel. But for now, it's just magnet is an object that attracts materials like iron, cobalt, nickel in the presence of magnetic field around it. Why does it affect iron? Because it produces a thing called magnetic field around its area, and hence because of that iron, cobalt, nickel gets attracted to it. So this magnet has two kind of poles. Let's say this is my magnet, half part of it will be north and another part will be called south. What is a north pole? Now we know our earth also has north pole and south pole. We know Antarctica is in south pole, Russia, Finland are in north poles. So we know earth has north pole and south pole because earth also has a magnetic field around it. Now, what are these north pole and south pole? So the north pole of a compass, of a magnet, of a compass is the end of that magnet that points towards the earth's north pole. Okay, and the south pole is the end that points towards the south pole of our earth. Okay, so these are two poles. Now a very interesting fact about these two poles are like poles attract each other. What does this mean? This means that if I brought another magnet near it, okay, if this is my another magnet, let's say if I brought the north pole near the north pole, so what it does, it will start to repel. It will repel each other, push each other away. But if I switch these poles, if from here, let's say this is now my north pole, this is my south pole, if I brought my north pole near my south pole, they won't repel now, they won't push each other away, they will pull each other to they will pull towards each other, they will attract. And so what we can say is like poles repel. Why? North and north are repelling, and unlike poles, that is north and south, they are attracting each other. Very basic, very things. Now you know what magnet is, what are the poles of magnet. Let's move on to a little bit harder topic, which is magnetic field and magnetic field lines. So you all probably are wearing Bluetooth headphones, right? Now if you go away into another or third or in your kitchen, then you will notice that the voice in your Bluetooth are getting abrupted. Okay, you will hear voice, and if you go a certain distance away, you will eventually notice that your Bluetooth will get disconnected from your laptop, from your phone, right? This is what? That is an area of our laptop or our phone inside which the Bluetooth will stay connected. Similarly, our magnets have an area around them. They have a aura around them, that in that aura, in that field of area only, they will be able to attract or repel the another magnet. Or we studied that it attracts iron, cobalt, nickel. So in that particular area, it will only attract or repel the magnet or the iron fillings or cobalt. If this is my magnet and this is my iron, if I place it here, it's getting attracted. But if I take it a certain distance away, the effect of magnet won't be visible on the iron. Okay, got that point? So magnetic field is the region around a magnet, like ignore this part for a while, we'll come back to this later. Why is it not working? We'll come back to this later, why we've written current carrying conductor. So the region around a magnet or a current carrying conductor where its magnetic field or magnetic influence can be felt, or within which the area within which a magnetic force can be experienced is called magnetic field, and we represent it by this symbol called B. Now we know that the unit of magnetic field is Tesla, on our very own brilliant scientist Nikola Tesla G. Now the next topic is magnetic field lines. Did you see in that video that the compass needle was getting, the direction of compass needle was getting changed when we switched the poles? When we brought south pole near the compass, the direction of needle was different. When we brought north pole near the compass, the direction of needle was different. It got reversed. Why it got reversed? Because of exactly the poles, but because of these magnetic field lines. We will know magnetic field lines will tell us what is the direction of magnetic field. We studied magnetic field. Now these magnetic field lines will tell us what is the direction of magnetic field around that magnet. In my magnet, will that magnetic fields will go from north to south, or will they go from south to north? Which is correct? So we need to understand which is correct. So magnetic field lines we make, so this arrow, this line I made around the bar magnet is my imaginary line. Okay, you don't see any magnetic field lines around the bar magnet, right? But I made these imaginary lines to help me understand what is exactly the direction of magnetic field around that magnet. So these are imaginary lines that represent the direction and strength of magnetic field. Strength, we are going to study that part. So let's study the main properties of our magnetic field lines. First and foremost, the very important one, you need to know the direction of magnetic field lines. Say this is my bar magnet, north and south pole. So always remember, outside the magnet, the magnetic field lines will always go from north to south, from north to south outside the magnet, and inside the magnet also they will travel inside the magnet also, and from south to north. Of course, to close the loop, if they are going north to south outside, they will go south to north inside the magnet. Very good, right? So the first part is done. Second point says, this is where we'll study the strength. Second point says, if my magnetic field lines are very near to each other, see, they are very close to each other, right? So these are close to each other instead of this, right? So where the magnetic field lines are very close to each other, there the magnetic field will be strong. But if they are far away from each other, the magnetic field lines will be weak. Correct? Third point, very important. Direction, we need to find the direction of magnetic field at any point, okay, and any single point. So what I'll do is, I'll take that point, I'll make a tangent. You know how to make a tangent, you've studied in math, right? I'll make a tangent on that point, and the direction of tangent will be the direction of magnetic field at that particular single point. Okay, at that particular single point, the direction of tangent will be the direction of my magnetic field. Now the fourth point is very important. This is very important. It says that the magnetic field lines, two magnetic field lines can never intersect. Why? Because we just know, let's say these two magnetic field lines are intersecting at this point. Okay, now if at this point, what did we study? The direction at any point is equal to the tangent to the line. If I try to make the tangent according to this magnetic field line, the tangent will be here, and according to this magnetic field line, on the same exact point, the tangent will be on downwards. But we know at one point we cannot have two tangents. That also we studied. At one single point, two tangents cannot be there. So that means that our magnetic field lines cannot intersect, can never ever intersect each other. Okay, this is a very important question that we also see in exams. Why do two magnetic lines can never intersect each other? Why? If two magnetic field lines intersect at a point, then there will be two tangents. You can just make this and then show this point, there will be two tangents T1, and at the same point there will be T2. Two magnetic field lines intersect at a point, then there will be two tangents at that one single point, and hence magnetic field will have two directions. Magnetic field will have two directions at one point, which is not possible. Of course, I can't go here and here at the same second, right? So magnetic field lines can also not go at two different directions at the same second, so they will never intersect. Now we need to study magnetic field lines of different types of magnets. Okay, let's say just a bar magnet for just an example. See, these are two parts of my bar magnet, a north pole and a south pole. What did we learn? The magnetic field lines will travel from north to south, okay, and inside the magnet they will go south to north. Of course, if I make another field line, then also it will also travel from north to south. Outside it will travel north to south from outside the magnet, and inside the magnet, the magnetic field lines will travel from south to north. It doesn't matter that the field lines are above the magnet, below the magnet, inside the magnet, outside the magnet. There is just one simple rule: outside north to south, inside south to north. That is your one simple funda. Straight wire we'll see just in a second. Okay, before that we have to see some other concepts. Let's go to them. Now the main part of the chapter has come. Magnetic field. Till now we have seen a magnetic field lines, the magnetic field effect due to just the magnet. Now what if someone gave me a wire and they tell me magnetize this wire? Okay, do something so that this wire acts as a magnet. Then how can I do this? Let me show you. Physics can make that happen. Okay, magnetic field due to a current carrying conductor. What does this mean? When I have a wire, okay, I have a copper wire, let's say, and current passes from copper wire, we know from electricity chapter. So I have a copper wire and I join an electric circuit in that wire. Okay, this is my copper wire and I have a key, I have a battery so that I can pass the current from that copper wire. And what I do is I place a magnet parallel to or under that wire, so that I can exactly know the direction of magnetic field, or where the magnetic field is going, how the compass is getting deflected due to that copper wire. Now what I did is I took a straight copper wire and is placed parallel to and over a compass needle. Then the deflection in the needle becomes opposite. Okay, so what is happening here? When I switch on my battery, okay, when I plug the key in, what will happen? A current will flow inside this wire. Inside this whole circuit, a current will flow, and inside this particular wire, the external wire that we connected, current will also flow. So what we saw was when we switched on the current, when we plugged in the key, current was flowing, the compass needle got deflected, which Hans Christian Ørsted saw already. But we are seeing a very interesting thing here. Here, what I did, now in this case, current is going from positive to negative. We know the direction of current. In this another case, I saw, let's switch the battery. Let's experiment and let's switch the poles of the battery. So what I did it, now instead of negative and positive, I switched the battery terminals and it's positive to negative. So instead of flowing downwards, the current is now flowing upwards. And in the wire also, instead of current is going upward here, instead of going upward, the current is now going downwards. So what we saw is, when the current was upward, the direction of needle was in a particular direction. But when we switched the direction of the current, the compass needle, the direction of the needle of the compass got reversed. If it's getting deflected towards the west, now it's instead of west, it's getting deflected towards the south. So we saw that the deflection in the needle becomes opposite when the direction of the current is switched, is reversed. So we know that not only we can produce a magnetic field around a current carrying conductor with the help of a current, we can also switch the polarity of our magnetic field. We can also make the compass switch the direction of magnetic needle with only the help of current, with only the help of direction of current. By just changing the direction of current, we can switch the direction of magnetic field. Let's go to the next topic, which says, now we have studied what magnetic field, how is current carrying conductor producing magnetic field. Let's see different shapes of current carrying conductors. We'll see first a straight conductor, magnetic field due to a current through a straight conductor. What we did is, we just took a simple wire, the same one, and we put that in a circuit. We switched on the battery, plugged in the key, switched on the battery, and now we have a current that is flowing through that wire. So what we did is, let's say this is my wire. Now I want to see the direction of magnetic field around this wire. So what I'll do is, I'll take a cardboard, let's say my hand is a cardboard, or let's say it's just my hand, and I'll sprinkle some iron fillings around this. We know iron fillings takes the shape of magnetic field around the bar magnet. Now I sprinkle some iron fillings. Iron fillings are small iron powder. We know magnet attract, or magnet has an effect on iron. So if I sprinkle some iron fillings, the pattern in which the iron fillings get produced, the pattern that produced is the pattern of magnetic field lines due to my straight wire. So I'll sprinkle the iron fillings, and what we saw is that iron fillings, these are the iron fillings, those iron fillings took the shape of concentric circles, like this. Concentric circles, all these circles have same center. So my iron fillings took the shape of concentric circles, which means my magnetic field lines around a straight wire also in the shape of concentric circles. So around a straight wire, magnetic field is in the shape of concentric circles. So we took a battery, consider a variable resistance, ammeter, plug key, everything. Now we connected a copper wire between 2 points X and Y in series with the battery and plug and key as shown. Now what we are seeing concentric circles. But how, now we saw that if we reverse the direction, if we change the distance, we studied that we can have an effect on these magnetic field lines or magnetic field with our current. So what are the factors here that we can change, that we can see the magnetic field strength is getting changed? First is current. Now if I increase the current, will the strength of magnetic field lines increase or decrease? Of course it will increase, right? If I increase the current, the magnetic field strength will increase. More the current, more will be the magnetic field. If I go far away, if this is my wire, okay, and it's producing some magnetic field on me, if I take this away from me, will it produce the same magnitude of magnetic field? No, right? It will produce a different kind of, a little less strength of magnetic field on me or the iron fillings, correct? So that's why here it's inversely proportional, okay? You can see here it's directly proportional to the current, but magnetic field strength is inversely proportional to the distance. Now we saw that when we change the direction of electric current, the direction of magnetic field lines also changes. That is the same here. If we change the direction of current, if I reverse the terminals of this battery, plus and minus, okay, the current will now flow downwards, it will flow upwards, and hence instead of, let's say, for now the magnetic field lines are going in this direction. If it flows upwards, it will flow, instead of upwards, it will flow downwards, okay? So change in direction of current changes the direction of magnetic field, but it does not affect the strength of magnetic field. It changes the direction. Instead of revolving like this, my magnetic field lines will start revolving like this, but they will be of the same strength. Their strength will not increase or the strength will not decrease. Okay. Moving on to the next topic, which is right hand thumb rule. Now we need to understand we studied the magnetic field due to a current carrying straight wire. Now we will see the next topic is due to a circle. Okay, instead of a copper straight wire, I'll give you a circle and I'll ask you, now you studied about the straight wire, now tell me what will be the magnetic field around this circular loop. So you'll get confused, ma'am, what is this? You are like a typical teacher. You studied, taught something else in the class, and you're asking something else in the paper. So for that, we need to study a very important thumb rule, which is right hand thumb rule. Very easy. What it says is, you take your right hand, you point the thumb in the direction of current. Let's say this is a wire and my current is upwards. This is a wire, let's say this stylus is a wire and it's upward. So thumb in the direction of wire, in the direction of current, and curling the fingers will give me the direction of magnetic field. If this is my wire, if I place my thumb in the direction of current and I curl my fingers around that wire, I curl my fingers, this is the thumb still in the direction of current. If I curl my fingers around the line, around the wire in which the current is running, then this curling, it's going from this side, this curling will give me the direction of magnetic field. This will be the direction of magnetic field if my current is going downwards. Now instead of upwards, I'll place my thumb like this and it's coming out of the plane. So this will be my magnetic field. In upward direction, it's going inwards. It's going inwards, outwards anyways, but if you see, it's going inwards, and in downwards direction it's coming outwards. Okay, understood? Very good. This is just a right hand thumb rule. Let's use this to understand, to find the magnetic field around due to a current carrying circular loop. So what we do is, basically in this is also connected to a circuit and a battery here. Okay, so we have current in this loop. What we say is, it's not getting to me. Let's say this is a current carrying loop, and if I zoom it, okay, if I zoom it and I keep zooming it, what will happen? Eventually at one point this thing, where is it? Okay, leave. At one point, what will happen? This curved wire, if I zoom in too much, this curved wire will appear like it's a straight wire. Let me give you an example. So you travel with your car and your scooty, right? Now we know Earth is like this. Earth is a sphere, we know it has curved surface, but you ever experience that you're going uphill and at some point you reach the height and you're going downhill in your daily life? Of course you go to mountains and all, but you don't see the exact curvature of the earth, right? Why? Because it has immense diameter. It's like we are living, but the point where I'm standing, it's like zoomed in, a lot zoomed in point. Okay, similarly, if I zoom this circular loop, what will happen? At one point, if I zoomed in and keep zooming in, the small point, this small point of the circular loop will appear to be a straight line to me. And we have studied the right hand thumb rule. If there is a straight line, just point the thumb in the direction of current, and the curling of fingers will give you the direction of magnetic field. So let's say in this case my current is upwards, or say not upwards, it's clockwise, correct? So if I zoom in, I'll see the current is in upward direction. If I hold this wire in my hand, the current is in upward direction. If I curl the fingers, the magnetic field lines are going inside, and from this point, this side, they are coming outside. Okay, so what is happening? If this is the point I'm choosing and this is the magnetic field, so at this point they are going inwards, right? They are going inwards, and outside the loop, inside the loop, the magnetic field lines are going inwards. Outside the loop, the magnetic field lines are coming outwards. Understood? See how easy it is. If you see this from a distance, you will see that this is such a big task. But if you zoom in, if you break it in parts, you will see there is a single small line that I can pursue as my straight wire, and I know the right hand thumb rule. I'll just put my thumb in the direction of current, curl my fingers, and this is the direction of magnetic field. Okay, you are saying this is in the upward direction. Let's take this part of the wire. Okay, if I took this part of the wire, now in that part the current is downwards, the current is downwards. Now this, my current is downwards. So instead of this, I'll hold my wire like this, thumb in the direction of current, current is downwards, thumb in the direction of current, and I'll curl my fingers, curl my fingers. So what is happening? See, I'm curling my fingers, and inside, this is the point we took, inside the loop, the magnetic field lines are going like this, which is inwards, and I'm curling my fingers outwards. So at outside the loop, it's again outwards. So did you see? If you take either this point or the diagonally opposite point, in both the cases, inside the loop, the magnetic field lines are going inwards, but outside the loop, the magnetic field lines are coming out. So we can just remember this for easy numericals or easy solutions in our paper, that when the current is clockwise, our magnetic field lines will be inwards inside the loop. Inside the loop, our magnetic field lines will be inwards, and if my current is anti-clockwise, now instead of flowing like this, my current is in the opposite direction. It's going like this, in the opposite direction. So this is my anti-clockwise. Let's take this part of the wire. Current is downwards and it's going inwards. This is going inwards from where? Outside the loop. Outside the loop, the magnetic field lines are going inwards, and inside the loop, they are coming outwards. Very good. Okay, and if you want, again take this part. Now the current is upwards and they are coming out. Now they are coming out from where? Inside the loop. They are coming out, and outside the loop they are going in. So outside the loop they are going in. So for clockwise, inside the closed loop, the magnetic field lines will go inwards, and for anti-clockwise, the magnetic field lines will come out from inside the loop. All these three things are very important. First, it's a closed loop. Second, you should know either it's clockwise or anti-clockwise. Then you should know inside the loop. You should mention inside the loop, these are either inwards or outwards according to the direction of current, whether it's clockwise or anti-clockwise. Now we are done. Again, now we need to know what are the factors affecting this. Of course, again, the current will increase, my magnetic field strength will increase. If I increase the radius of this, if instead of this small loop, I increase the radius of my loop, the magnetic field strength will get decreased. It will decrease if the radius of the loop increases. So it's inversely proportional. Now, if I'm at this point, then the magnetic field strength will be more. If I go till here, the magnetic field strength will decrease. So again, it's inversely proportional to the distance from the loop. Very good, very easy. Let's see. Okay, now we have seen the magnetic field due to a straight wire and a circular loop. Now this is a very important, very important, almost every year, not almost every year, but a lot of times on alternate years, let's say, or even MCQs, in some kind of way a question has been asked from this topic because it's very important. What is it? A solenoid. The magnetic field due to current in a solenoid. First we need to understand what is a solenoid. So you took a wire, you took a coil and you turn it in many circular loops, okay, like this. See, this is my wire and I rounded it, turned it into, circularly wrapped it into many circular loops. Which wire are we using? Insulated copper wire. Which wire? Not just a copper wire, insulated. It should be insulated copper wire. This is a very important keyword of this concept, that a coil of many circular turns of insulated copper wire wrapped closely. Now when we are wrapping these circular turns, they should be very close. There should be no distance. If you can see some distance in it, it's because we need to understand that these are different circular wires, different circular loops, not just one. But in practice, when you wrap an insulated copper wire in many terms, they will be wrapped really closely and there will be negligible space in between them. Okay. Then the shape of a cylinder. If you wrap those circular wires, you will get a shape of cylinder. Then a shape of a cylinder. That shape of a cylinder, due to an insulated copper wire, is called a solenoid. And this wire is connected to a battery, is connected to a key, and all that stuff that we need to pass current from this wrapped closed wire. Okay. Now what we do is we switch on the key. What will happen? That this side of the battery is positive. This will be our battery. Okay. Now this side is positive. The positive side, when we pass a current from a wire, we know it shows magnetic behavior. We shows it create magnetic field lines around it. Okay. So for magnetic field lines, if it's behaving as a magnet, it will have a north pole and a south pole. Now, very important, if the positive side of our solenoid, positive side of our battery will create south pole on our closely wrapped copper wires, the positive side will have south pole and the negative side will have north pole for the solenoid. Correct. Now we know that magnetic field lines, ma'am, they travel from north to south outside the magnet. So these are traveling north to south outside the magnet, and inside the magnet they are traveling from south to north. Can you see? They are entering into the south, exiting from the north. They are exiting, they are going outside, they are exiting from the north, going inside from the south, which explains our theory of the magnet, that for a magnetic field lines travels from north to south outside the magnet, and inside the magnet they goes from south to north. Now very important point here, that there will be lots of magnetic field lines like this one, this one, all this stuff. Now what's important here to remember, that inside the solenoid, when we are wrapping the wire, we are just wrapping it around air. We don't insert anything inside it. So inside that copper wire, inside that solenoid, the magnetic field lines will be uniform. They will be uniform. But outside the solenoid, they will start dissipating from each other. Like they will increase the distance among each other. The distance of field lines, magnetic field lines, will keep on increasing. Hence, outside the solenoid, the magnetic field lines will not be uniform. They will be non-uniform magnetic field lines. So remember, this is a very important question. Overall, including outside and inside of the solenoid, overall the magnetic field of a solenoid is non-uniform. But inside, if someone asks you what is the magnetic field inside the solenoid, uniform or non-uniform, you will say it's uniform. Why? Because it's inside the solenoid. Outside the solenoid, the magnetic fields will not be uniform, they will be non-uniform, and hence overall also the magnetic field of a solenoid is non-uniform, but inside it's uniform. Okay, understood? Now again, for solenoid, we will also see what will be the factors affecting the magnetic field due to this current in a solenoid. So the first is simple. The current increases, the magnetic field strength increases. Now, if the number of turns of this copper wire, how we made a solenoid? We took an insulated copper wire, we wrapped it. Okay, if the number of turns are 10, there will be a 10 units, let's say, magnetic field strength. If we increase the number of turns of that insulated copper wire to 20, the magnetic field strength will be directly proportional. It will also increase as the number of turns in solenoid increases. But we know if I go away from the solenoid, the magnetic field strength will decrease, and hence magnetic field strength or magnetic field is inversely proportional to the direction from the solenoid. True. Let's move on to the next. This again very important topic, electromagnet. Now I had a solenoid. I took a insulated copper wire, wrapped it. Now if I wrap that insulated copper wire around a soft iron, what I wrap it around? A soft iron core, then I pass the current in that solenoid, in that wrapped copper wire. Then because of that current, this soft iron will become a magnet. It will start behaving like a magnet. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material, which is soft iron, when placed inside this coil. I have this coil and this is my soft iron. This is my soft iron. I placed it inside that insulated copper wire and I passed the current through it, and what do I see? I see that the soft iron is now behaving like a magnet. It is now behaving like a magnet. But a very important point, there is a word written temporary magnets. Why? Because as soon as I switch off this current, as soon as I pull this plug out, this soft iron will stop behaving like a magnet. It will behave like a magnet only till the current is flowing, and that's why, because it's becoming a magnet due to an electric current, we call it electromagnet. We have given it the name electromagnet, and this magnet formed is called electromagnet. Very simple, very easy. Now we studied about solenoid, and we also studied where we can use that solenoid to make a non-magnetic material to make it behave as a magnet, and we use soft iron for this. Now some of the last important topics. This is a very important difference. They might ask you in paper that what is the difference between a temporary magnet, a permanent magnet, and this is of course temporary magnet, right? So permanent magnet is permanent, but a temporary magnet or electromagnet is temporary, because as soon as we switch off that plug, pull that plug, we switch off the current, this will stop behaving like a magnet. Okay, then the second point is the permanent magnet has a fixed strength. It does not vary if the current is more, if the current is less. A magnet, if it has 10 Tesla of magnetic field strength, then it will remain 10 Tesla for its life. But for electromagnet, we see that if we increase the current, the magnetic field will increase. If we decrease the current, the magnetic field strength will decrease, and hence it does not have a fixed strength. It has variable strength. Variable means it's fluctuating. It can variable. Then it has fixed polarity. Now we studied one more thing. If I switch the terminals of the battery, the direction of current will get reversed, and hence the direction of magnetic field lines will also get reversed, and hence the polarity means in which direction my magnetic field lines are moving from north. Of course it will go from north to south, from upwards, downwards, inwards, outwards. That is defined by polarity. So for permanent magnet we have fixed polarity, but for electromagnet, if we reverse the direction of current, we will get reversed polarity, thus it has variable polarity. Now we studied about all these things. There's just one topic mainly that is left, that is force on a current carrying conductor. Now we know Ampere G. He said that when this current is flowing through a wire or a conductor, it is not just creating magnetic field around it, it is also producing a force. Or we are saying that if we place that current carrying conductor inside an external magnetic field, this is a horseshoe magnet, if we place our conductor among or inside a external magnetic field, then a force will be experienced by that conductor. So both is true. The conductor will also produce some force around it, and the external magnetic field will produce a force on that current carrying conductor. A current carrying conductor experiences a force whenever it is kept in an external magnetic field. Now here again, the direction of force can be reversed if we reverse the polarity, if we reverse the terminals of our battery, hence changing the direction of current. And there are some examples of this are electric motor, loudspeakers and electric generator, etc. This is one topic that you should remember, that a current carrying conductor placed in an external magnetic field will experience a force due to that external magnet. Very good. Now next topic. This is again a very important topic. One of the most important topics of this chapter is Fleming left hand rule. What we studied, that we have a conductor and the conductor will experience a force, or the current carrying conductor will experience a force due to the external magnetic field. Now this is a rule which tells us that in which direction that force will be experienced, upwards, downwards, outside of the plane, inside of the plane. Okay, let's see. Take your left hand and make the 90-degree angle in between your thumb, your index finger and your middle finger. Stretch these and make an angle of 90 degree, like this, 90 degree among each other. If you do that, you will see that your thumb is pointing towards the direction of force. It will give us the direction of force. How? When your index finger is pointing towards the magnetic field and your middle finger is pointing towards the direction of current. The middle finger towards the direction of current, the index finger towards the magnetic field, and your thumb will hence give us the force. This is called Fleming's left hand rule. Correct? Let's see. We'll see a question on that later. Just give me 2-3 slides. Now we have electric wires in our houses. We know current is coming, current is going and all. There are some certain terminals, or there are certain colors of wires that are defined so that we don't get confused that which wire is pulling the current inside the house, which wire is throwing it away outside the house, and which wire is neutral and all. So let's see. We have 3 kinds of wires that operate this whole procedure of electric current in our houses. First is a wire of red color, and second is black color, third is green color. The red color wire is called live wire. Remember, it's called live wire and it's of positive. And what it does, it carries the current from outside of the house, from some pole or something, and it brings it to our house, and then we use it in certain appliances, in our bulbs, in our ACs, etc. Okay, then we have black wire, which is neutral wire, which is negative. Now it completes the circuit. How? See, we have this plug in our houses. Okay, now this plug is of red color, not red color, this plug is of red wire, and this plug is of our black wire, and then this plug is of earth wire. So what is happening, what we usually do when you put a charger inside that plug, you usually put this in these two terminals, right? So what is happening, we are putting a charger in between a neutral wire and a live wire. They are never connected directly with each other. The positive wire and a neutral wire will never be connected directly with each other, because if they do, there will be a spark, there will be a short circuit in our houses, which we'll study just in the next slide. So what happens is, this is our neutral wire, red wire and green wire. Now this red wire gets the current from electric pole to our houses. This black wire takes the current, excessive current that was left, and throw it outside our house back to the electric pole or the source where it came from. Now this earth wire, what it does is, let's say you have a metal conductor. We used to have those coolers in our houses. I don't know if you guys have them anymore, but we used to have those metallic coolers in our houses. And when you plug in the cooler, and there is a supply of water in it, so what is happening, that particular metal box is getting water inside it and it's getting electricity inside it, so it's a danger because of electricity and water. So what happens is, if you see in those metallic coolers, you will see the plug will not be a 2-switch plug, it will be a 3-switch plug. Why? Because the third switch used to go inside this earth terminal. It connects to the earth wire. What it does is, it connects the extra charge, on the metallic body of the cooler. The charge which got out and is now residing on the metallic body of the cooler, and if you touch it, you get an electric charge, electric current. It's because there is some charge on the outside metallic body of the conductor. So what it does is, it connects the electrical appliances metal case to the earth, passing the leaked charge to the earth. Now earth is like, it's like a mother. How much charge you will give to earth, it will neutralize it, it will accept it. So what we do is, we connect all that extra charge from the metallic body, we connect it to the earth wire, and we pass it down into the earth. Inside this switch, you will see that this wire connects directly into the earth. There is like a metallic box inside the earth. We connect it to that, and hence we do not experience any electric current because only of this earth wire, this green wire. Okay, done. Now there are two kinds of current that we get in our house that exists. One is AC, one is DC. In our houses, we usually get AC current. Now AC current, why we get AC current? Let's study about what is AC current. So alternative current is, it changes its direction periodically. If I want to make a graph, like this is my AC current. One cycle comes, the other cycle goes, it's positive, it's negative. This is my AC current. But in DC current, it has fixed direction. So this is my DC current, this is my DC current, or if you want to make like this, this is my DC current. It has a continuous supply, wherever AC, it has a fluctuating supply. So it is changing its direction continuously, but my DC current is not changing the direction continuously, it has a fixed direction. Again, the magnitude of my AC current is also getting changed. It's increasing, goes to a higher point, decrease, 0, then goes to the negative, goes to the maximum negative point, then comes back to 0. Okay, so the magnitude is also continuously changing, but in DC, it just has fixed magnitude. If it's 10 units, then it remains 10 units till the time it's flowing from our circuit or a wire. Okay, now in our household circuit, we usually get a power supply of 220 volt, but in DCs, we get the DC current from batteries, from cells. Now why is AC current good? Because it has less power loss. Okay, if my supply is coming from electric pole or electric house which is 20 kilometers away from my house, the electricity needs to travel from the 20 kilometers to my house. So in that span of time, this AC current does not lose its power, lose very less power. But DC current, it loses lots of power in transmission. That's mostly the reason why we don't use DCs in our houses. Also, it has fixed magnitude, so that cannot be a good thing. AC current has variable magnitude, variable direction. That's why we use them in our houses. Now, in my mic that I'm using, and probably my camera, in your cameras, we use DC, we use batteries, we cells. So it's not like every time AC is better. AC is better because we need longer transmissions for our houses, and because of the longer transmission, because of the less loss of power in AC current, we use that in our household circuits. Very good. Next is I told you there will be a question from Fleming's left hand rule because it's very important. I've also made a 5-minute 5-mark video on this Fleming left hand rule. Well, of course I explained it, but there will be a question, a PYQ on 2 PYQs, 2 or 3 PYQs in that video. It's just a 5-minute video. You can go watch it and you can put your 5 marks in your pocket. Just saying. Okay, an electron enters a magnetic field. My electron, this is my electron, it entered a magnetic field. The direction of force, what we need to find? The direction of force, and we know that we found the direction of force. We can find the direction of force using Fleming's left hand rule. Force, Fleming, you can remember that, okay? FF, direction of force, Fleming left hand rule. So what we'll see is, this is my left hand. Now this, my middle finger will be in the direction of current. Like for instance, this is electron, so we know usually the direction of current is opposite to the direction of electron, but we need to know what is the direction of force on this electron. So for now we can just take direction of electron as the direction of our motion of charge. So this is my current or motion of my charge. This is my magnetic field. This index finger gives the magnetic field, middle finger gives the current. So my force is, my thumb is giving the direction of force, which is outwards. Okay, it's giving outwards, and this is out of the page. Hence the question, a very important question. This kind of question has come in the previous year's questions in your boards, 10th boards. So do not forget to revise Fleming left hand rules, do the PYQs. These are very important, okay? PYQs is like your Ramban. If you do all the PYQs, which we are bringing a series very soon on our PYQs, will be going live to solve 1 marker MCQs, because on the basis of the new pattern of CBSE, most of the paper will be competency based. So we're bringing live for you guys so that you can ask your doubts, you can solve those questions with us on live, and we'll also making videos for you guys for 2 marker, 3 marker, 5 marker as well. So make sure to subscribe the channel. You can also join our WhatsApp channel. That link will be also given in the description, so that you don't forget, you don't miss these kind of videos which are very important. You will get continuous notification, and if you revise these just 2, 3, 5 marker PYQs, competency based questions, you will be all sorted. You will be just fine, okay, for your pre-boards. Now a very important question we are done with. Now just 2 more topics left. One, what is short circuit, what is overloading? Directly they give you question in CBSE 10th boards, what is short circuit, what is overloading? No question where they wrap it around all the concepts. No, directly what is short circuit, what is overloading. So let's say what I said is my neutral wire and red wire, my neutral wire and my positive wire, they are never connected to each other, okay? We connect a resistance inside it. What is resistance? Our charger, our appliances, our iron, cooler, AC. All these are connected between a live wire and a neutral wire. But if by chance they get connected together without any resistance, my neutral wire and my live wire gets connected to each other directly, then what will happen? A lot of current will flow in that circuit. It will cause sparking, it will cause heating, it can even result into a fire hazard. So a short circuit happens when the live wire and my neutral wire comes into direct contact, allowing a large current to flow suddenly through the circuit and hence causing heating and hence causing a spark, hence causing a fire. So keep a notice that you never connect a live wire directly to a neutral wire, that is a red wire to a black wire. Never connect those wires directly, okay? Then what is overloading? Overloading occurs, say my appliance needs a current of 15 ampere only or 5 ampere, and from behind a current of 15 ampere comes. So what will happen? That appliance will not be able to handle that much current, right? So it will not be good. So it occurs when too many electrical appliances are connected. Also, you can say that you have seen that multi-plug pin, right? So if my current is just coming 5 ampere and I'm putting that plug and a lot of, even my fridge, my computer, my charger, all are connected just in that one plug. So that is called overloading, which occurs when too many electrical appliances are connected in a single circuit, drawing more current than the circuit's safe limit. More current, circuit safe limit is 5 ampere, but I've connected fridge and TV and AC, so it's getting more current. It wants 15 ampere. But it's only getting 5 ampere, so it will result into overloading, which is more than the 15 ampere is obviously more than the circuit's safe limit, which is 5 ampere. Now next is our household circuit. So just normal, what we said, a live wire comes which is of red color, this is of red color, and this gets connected to all the all the switches in our houses. This is neutral wire which is of black color, this is earth wire which is of green color. Just a second, this is of green color, okay? So what happens is, this live wire, this neutral wire, this is our electricity board's fuse. So we studied about fuse in electricity chapter, right? We connect it in series before our actual appliance or actual switch, so that if extra current comes from the electricity board, electricity house, then this fuse melts because of the extra current, because if the current is more than the safer limit, this fuse melts, breaks the circuit, cuts the electricity of our houses, and hence it protects our appliances. It protects the appliances of our houses by cutting the supply of extra current. If my fridge needs 10 ampere and from behind 15 ampere comes, and the safe limit of fuse is, let's say 9 ampere or 10 ampere, exactly same as my fridge. So if more current than 10 ampere comes, then my fuse knows, oh shit, my fridge only can handle 10 ampere. If I give 11 ampere, it will crash. So what I'll do is, the fuse gives its baldani, what is it? The fuse melts, it burns and it cuts the circuit, and hence it protects the fridge from getting extra current. So this is our fuse. Now this is our electricity meter that we have in our houses, the main electricity meter outside of our houses, right? Now this is the distribution box. So we have one electricity meter and different switches for each our room, our kitchen, bedroom, hallway, right? So this distribution box then distributes the wire again in different switches. Each switch has a live wire, each switch has a neutral wire, and each switch has a earth wire connected to it. The power we get in our houses is 220 volt. The current we get is between 5 ampere to 15 ampere. Because our microwave oven, a fridge might need more current, so in that cases we use bigger switches, right? So we can get more current in those switches, and for normal ones we can get lesser current, like our charger, our TVs and all. So this is our household circuit completed and done, and I guess this is where we complete our one shot of this very important chapter, magnetic effects of electric current. Again, I urge you to join our WhatsApp channel so that you keep getting notifications of these very important videos of all the subjects. We are bringing live PYQs, we are bringing 2 markers, 3 markers very soon, which will be very important for your boards and your pre-board, so you don't want to miss those videos. So highly suggested to check out the channel, subscribe, join our channel, and also these videos we are putting so much effort for you guys. We're making one shot rapid revisions, 5-minute 5 markers, we are bringing live PYQs and all. So go ahead and subscribe the channel so that you don't miss any of the videos. This is your Ramban. These videos are your Jadi Booties to clear your boards with flying marks, with 90%, 95%, whatever is your target. Follow our channel, subscribe to our channel. You'll also get strategy videos, how to study, how to not waste time, how to not feel sleepy and all, which are very important for you guys. And we'll come back, we'll meet in the next video. Till then, tada, bye bye.